Okay. This moves like an alligator or like a crocodile. So this is completely developed at IIT Patna. We will discuss the design details of this in the afternoon session. Right now we'll just see some videos. This is a stair climbing robot. So here the robot has 3 degrees of freedom legs. There are 4 legs, so there are 12 degrees of freedom. And this robot can climb stairs. So you can see that the robot is automatically deciding which joints to move in order to climb the stairs. This is a fish robot. So this fish robot moves its tail fin, or what is also called as caudal fin. It oscillates it and thereby it generates thrust, and then it moves forward. This is a snake type of robot. It's a caterpillar robot actually. Okay. So you can see that this robot has many revolute joints, or revolute joints means the joints that allow rotational motion, which are driven by these motors, and then these motors move in an alternate manner, right? So that movement in an alternate manner is decided completely by the computer that is on the robot. This is another robot which swims in a water. It's like a snake type of robot for water swimming. So here you can see that this robot can take a left turn, right turn, and it can also go through some path. So you know, it will go through these balls. This is another wheeled robot. So this robot operates on wheels, and it can move around and say get information from the surroundings using an onboard camera. Okay. So any questions so far? Okay, so now you must be wondering that so fine, we have seen these many robots. Yes.
Sir, is there a fixed number of decisions that could be implanted in a robot while making the whole system?
Yeah, right. Good question. So he's asking that will there be these decisions already coded up on a robot, right? That's what you are asking, right? So or the robot can make new decisions also, isn't it? Yes, the very basic kind of robots will have the things coded up on the robot. The code should be already there, hard coded. But these kind of robots that you have seen, they have sensors on it. And depending upon what input we are getting from the sensor, the behavior of the robot will change. Okay, so in a sense, yes, the codes are there, already there, but those codes have some variables, and these variables can actually decide the behavior of the robot. So now you must be wondering that these robots, how they are actually made, like they move around in an interesting way, but how are they actually made? So overall construction of the robot is not just the hardware part of it, right? There is a hardware and then there is a software on it, right? So broadly, if you see, on a mota moti तौर पर अगर हम देखें उसको at a broad level, then there is a hardware layer and there is a software layer. On the hardware layer, there is a robot structure. Okay, so robot structure means that it will have links, it will have joints, and so on and so forth. Okay, like for example, that swimming robot that you saw, it has many links, and those links are joined by joints. But that alone will not make this robot move around. We need these joints to be operated by some motors or by some actuators. So there are actuators. Now these actuators will not move by themselves. Even if you power them, you need to move them in a very specific way, right? So that is decided by microcontrollers. And the microcontrollers receive the signal from sensors. So sensors means that, the camera is seeing around what is happening, and based upon that it is generating signals for the motors to make them move in a specific way. Okay, so that's the hardware layer. Now at the software layer means, you have the hardware, the microcontroller, which can have a code that can generate signal in a very specific way. But what should that code be? What should that software be? Actually, that software itself has different components. Okay, so it will have a controller component. Controller component will decide how to convert the sensor information into signals for the actuators. Okay, so for example, let us say that there is a wheeled robot which is moving on this stage, right? And then there is suddenly an obstacle. Say I am standing in front of that robot. So the robot has these wheels, and the wheels are run by motors. And as soon as the robot comes in front of me, it should stop. So how does it work? The camera on the robot will take an image continuously, right? And as soon as it sees an obstacle, it will keep performing image processing, and as soon as it sees the human in front of it, it will stop the motors. Okay, it will stop the motors. It will stop running the motors. So this aspect is known as control, right? So whether it is obstacle avoidance, whether it is movement, all of that is done using control. Then there is a planning layer. So when the robot sees the obstacle, it stops, right? But if the robot has to move from one point to another point, and there are many obstacles, how should the robot decide to move around, right? Whether it should, when it sees the obstacle, whether it should take left or whether it should take right. That aspect is decided by planner. So the planner should make a plan in such a way that it is optimal, right? Means, what is mean by optimal? Optimal means that the time taken is minimum. Okay, the power consumed is minimum. Okay, so whatever we are interested in to save, that is saved by the planner. So if we are interested in saving time, then the planner will make a plan which saves the time. For example, let me give you an example. Say if you want to go to Delhi, right? If you want to go to Delhi, there are so many ways, right? One way is that first you go to Jaipur railway station, and then from there you catch a train, and then you go to Delhi, right? So that is one way. Another way is that you take a taxi, go to the airport, take an aeroplane, go to Delhi. Or you just walk there. Right? Let's say these are the three options. There are many other options, but these are the three options. Now, if I give you the objective that I want to save money, I don't care about time, I don't care about effort, I want to save money, which is the optimum solution? What do you say? Huh? Getting bus from the gate. But I gave you three options, right? Option number one is where you take a train, The second option is you take aeroplane. The third option is you walk all the way to Delhi. So if I want to save money, then what should I do? Okay, walking may be an option, but there may be health impact and maybe my health get degraded and then I may have to spend money and all that. There are other issues like that, but yes, you are right that walking can save money. But if I am giving you the objective of saving time, then aeroplane will be the solution, right? And if I give you the option of saving money we have already covered. Say we want both, means we want to save money and we want to also save time. Then maybe train will be a better option, right? So it depends upon what objective we set, that what solution we will get. Okay, whatever objective you will set, based upon that you will get the solution. So planner does exactly that. As a user of the system, if you are using a robot, you will set the objective in the planner and planner will convert that objective into a plan. Like you did just now. I give you an objective, right? I gave you an objective that I want to save money and you made a plan for me. You said you walk, right? It's with a very simple example. So then there is mapping. So the robot should also know about what is there in the environment, right? The robot cannot move around without knowing where the obstacles are, where the goal is. So that thing is done by mapping part of the software. You might have heard about, or if you haven't, you can do a Google search later on SLAM, simultaneous localization and mapping, SLAM, right? So SLAM is a software component which does the mapping and localization together. Now let's look at each of these components little bit in more detail. So first let us talk about environment. See, robot operates in an environment, right? I showed you various examples. So I showed you a robotic boat moving in water, for example. So there the environment is, if the example is robotic boat, then what is the environment? Water, right? Water is the environment. Now the way the interaction between robot and water happens is very peculiar. When the robot moves in water, the water gets displaced, right? Water is moving, and when water moves, it also influences the robot. So these interaction between the environment and the robot has to be considered while developing the software, the intelligent software. Say if there is a robot which is pushing the things around in this room, okay, in order to move them from one place to another place, then as the robot pushes things from one place to another place, the environment changes and it has to know that it had moved. For example, see, if I had a chair over here and I moved this chair here and then I started talking to you like this, and then without realizing that I moved chair here, I moved back like this, then I would fall down, right? So I would have to remember what I did in the environment in order to move in a safe manner. So likewise, the robot also has to consider the influence of the environment on the robot and its own influence on the environment and their mutual relationship. Here I'll show you some of the different environmental effects. So here you can see the water as an environment. So this robotic boat is interacting with the water environment. Now what you can observe here is, if you command this robotic boat to go straight, because of the wave, the boat will deviate, right? So therefore the command that is running the robot, it should have that component which looks at the wave, and based upon that it takes more compensatory action. So if the wave is pushing me in this side, on this side, and if I have to move that way, or rather I have to move straight, for example, then I cannot move straight, because if I move straight, because of the wave, I will eventually end up here. So what I'll have to do, I'll have to move this way. When I move this way, because of the wave, I'll eventually move straight. Got it? So this logic has to be incorporated, and that is a part of, again, intelligence of the robot or artificial intelligence. Here at the bottom left, you can see this robot following a human. Okay? So now this particular robotic vehicle moves on wheels, whereas the target human is moving on legs. So the capability of legs is different compared to wheels. For example, with legs one can jump from one place to another place, right? But wheels cannot jump. So the wheeled robot has to actually move in a way that it avoids the ditches, even if the target person is jumping over the ditches. Means say, see, if the program that you have written on the robot is very simple, it only chases the human, right? It always follows the human, then it will very soon fall into the ditch. So it should have that intelligence, that not only that it looks at the target, but it also considers its own capability of wheels. समझ में आ रही है बात? Wheels, because of wheels, it cannot jump just like humans, so it will take a turn. And then we have these moving obstacles. So in an environment there can be huge number of moving obstacles. Like in this environment you can see there is a huge, you can say factory floor cubicles, and there are other moving objects, and because of those moving objects, the robot, if you see the real robot, it has to actually avoid the obstacles that are moving around, right? So again, there has to be an intelligence on board on the robot that decides how to avoid the obstacles. And here on the bottom video, you can see there is a robotic boat which is chasing another boat which is driven by a human. So basically, you know, the boat which is target boat is driven by remote control, and there is another robot which is following it. So that following motion again should have an intelligence which should detect, you know, how the human is actually moving this robotic boat. So that means that, you know, in all these examples that I have shown you, there is a component of autonomy in there. Autonomy, right? So autonomy means what? Say if I ask you to get a computer right now, right? If I ask you to get a computer, so maybe your computer is in your room somewhere, right? So I just ask you to get a computer, and you will decide which door to exit first, right? And then how to move to your room, and then get your robot and come here, right? And on the way, there may be obstacles, there may be different things, vehicles moving, and how to save yourself. So you are an autonomous agent. I just give you a command that bring a computer, and you decide, you know, your small actions, like how you should move, how you should save yourself from other vehicles, and how you should get to the target and perform the mission, right? I do not have to tell you first, get up on your feet, move left, move right, you know, that's kind of very difficult, right? So in a robot, we would like it to be autonomous, means we give it a high level command that avoid obstacles, and it should avoid by itself. It should make decisions by itself. So autonomy is at two different levels. Now this is something important, you know. If you ever think of programming a robot, right, you have to think about at what level you want to impart the autonomy. At what level, right? So there are two levels. First one is reactive autonomy and second one is deliberative autonomy. So what is reactive autonomy? Let me explain you. Say you are walking on the road, you are walking on the road and a person is running in opposite direction, okay? And that person is just, you know, appearing in front of you suddenly, okay? So what do? You will avoid that person, right? So that you don't bump into it, you don't bump into that person. So you will either take left or right, you will take one particular action, okay? So that is known as reactive autonomy, means you react to given stimulus. So this type of autonomy when built on a robot, when you know, you program on the robot that if there is a danger, then what it should do instantly. That is reactive autonomy. It is implemented using perceive, think, act loop. Okay, perceive, think, act. Perceive, think, act. What is perceive? The robot perceives using its sensors. So say if there is a camera on the robot, it will get the image and it will process the image, and based upon that it will perceive. It will make a perception model. Okay, and then it will think. So based upon whatever data it has gotten from the sensors, it will then think. Think means it will make a decision, you know, whether to turn left or right or whatever. And then act. Act means it will take that action. And when it takes that action, it moves. And then again it perceives. And it keeps running this cycle. Perceive, think, act, perceive, think, act, perceive, think, act, like that, right? So that is reactive autonomy. On the other hand, say you are playing the game of chess, you know, game of chess, right? So there, how do you work? How do you move your coins? When the opponent is, you know, striking one of your pawns down, then do you act just instantly based upon that, or you think that, you know, if I take this action, then what my opponent will do, and then I will do what I will do, and then what opponent will do. So you think like that, or you think, you know, whichever pawn comes in front of you, you strike it out. Which one do you follow? Yes, deliberative one, right? There, the thinking is to be done at a deeper level. Deeper thinking means, you know, actually it is like there is one action that you take. Based upon that, there are possible responses. And based upon those responses or states, you again take certain actions. And then based upon those actions, certain other responses. So deeper you can think, better a chess player you will be, right? The grandmasters can think up to 15, 20 different depths down in any game, and that's why they win mostly. And computers can actually sometimes outrun even grandmasters, because they can think much deeper depending upon how much memory capacity that computer has, right? So in the case of robots, when there are missions of high importance, then deliberative autonomy is important, right? So say for example, there is a robotic boat which is protecting a target, which is protecting a valuable target. Like let us say there is an oil tanker in the ocean, and the robotic boat is trying to protect it from intruders. So there it has to make strategies. You know, the robot has to make strategies to protect it. So it has to make deeper thinking. In fact, in any robotic system, a combination of deliberative, that means deep thinking, and reactive or shallow thinking is done. For immediate actions, reactive autonomy is done, and for missions, deliberative autonomy is done. So let me ask you a question. Say you want to develop a robot. Let us say you want to develop a robot in your campus, okay, which takes you from one building to another building. Like for example, some of you have come from some other building to here on a vehicle, and which is driven by a human. So you want to convert that into a robot, right? So what kind of autonomy that robot will have? Reactive or deliberative? But it will be more towards reactive or more towards deliberative? Yeah? As I said, reactive and deliberative, these are concepts, so your autonomy will be somewhere in between this, right? A combination of this. But a simple robot which is just taking you from one building to another building, will it have more of a deliberative type of autonomy or reactive type of autonomy? Reactive type of autonomy, very good, right? On the other hand, let us say that you want to develop a security robot. You want to develop a security robot on an airport, which should find out if terrorists are going to attack and then to subvert their attacks. So there it should be more of reactive, or it should be more of deliberative? Deliberative, right? So now if you can recognize these two differences, then you are like, you know a little bit more about robotics actually. Okay? So now let us look at one of the crucial aspects of robotics, which is called as locomotion. So all robots have to move, right? You remember that we defined robots to be something which actually move from one place to another place. So locomotion is an important aspect. Locomotion means moving from one place to another place. Is an important aspect in robotics. So can you tell me how old our planet Earth is? Just a guess. Like it has never, it's not that it has been ever forever, right? It has been there forever. You see, it's about 4.5 billion years old. Okay? It's based upon the different types of geological studies that people have done. They find that Earth was a hot gas of hot balloon of gases in the beginning, about 4.5 billion years ago. Okay. Now, in the beginning, when it was very hot, there were no life forms, right? There were no life forms. So first life forms emerged about 3.6 billion years ago. 3.6 billion years ago. At that time, these things were very small prokaryotes, cells which would just drift around by the currents in the water, right? And then the first time locomotion was observed was about 500 million years ago. So what I want to tell you by this timeline is that about 4 billion years were spent in forming lives on Earth, right? And then in 500 million years, different forms of locomotion evolved, right? So swimming, walking, flying, and all these things emerged in 500 million years ago. That's a long time, right? And this is based upon one simple principle in biology. Do you know what that is? Evolution, survival of the fittest, right? Survival of the fittest. So these locomotion that you see around yourself, right? Say you are looking at quadrupeds. Quadrupeds means animals with 4 legs. So they move around, or you see birds that fly, aerial locomotion, right? or you see fishes that swim. So these are all, these have all evolved for enhancing the survivability. Because these creatures could move around, they can get food, they can protect themselves from predators, right? So, so that way survivability is improved. Now, another thing is that these locomotions have evolved on the surface of Earth, and if we want to develop a robot that should move on the surface of Earth, then it's kind of quite natural to take inspiration from these creatures, right? How these creatures move, if we copy it into machines, then the chances of these robots to be successful on Earth will be much better, right? You know, it makes sense to take some inspiration from different creatures, and this principle of design is known as bio-inspiration. So if we copy, for example, from quadruped animals like a dog, and we make a machine out of it, then we say that we have taken a bio-inspiration. So the picture of big dog that I showed you, that is a bio-inspiration. The biped means two legs, right? Two legs. So the Eskimos picture that I showed you, Eskimos video, that is again a bio-inspiration, right? So in fact, all the robots that you see is one way or another is a bio-inspiration. Even those manipulators which move, you know, pick things up and move, they are inspired from human arm. So let's look at these different types of locomotions, right? So legged locomotion. Legged locomotion are broadly of two types, okay? One category is where they are based on 4 legs, called as quadrupeds. And another one is based on 6 legs, which is usually found in insects. So 4 legs are usually found in mammals and reptiles, and 6 legs are found in insects, right? So if there are more number of legs, then the stability of locomotion will improve or reduce. What do you say? If there are more number of legs, then the stability will improve or degrade. Yes? Improve, right? Let me give you an example. Take the example of a human baby, okay? A deer baby or deer cub, and an insect like spider, right? So as soon as an insect hatches the egg, it will start walking as soon as it hatches the eggs. If you look at a deer or a cow calf, when it is born, after 15 to 20 minutes, it will stand. How about a human baby? It takes months for it to even learn to stand, and then more than a year to start walking, right? So why is that happening actually? Why is that happening? See, in insects there are 6 legs, right? So 6 legs give you stability, okay? In fact, for static stability means something which is not moving. When you give it some impulse, when it is at a state of rest, you need 3 points of contact, minimum 3 points of contact. Like this table, you know, this small table over here, it has 4 legs, right? Even if you remove 1 leg out of it, based on the 3 legs, it will be in static equilibrium, okay? Static stability. Now, if there are more than 3 legs, then there is more stability. In fact, more the number of legs, stability will become better and better. right? So how do you define stability? How do you define stability? Let me tell you. See, if you take any object, say something which is like like this table again, it's not moving right now, right? It is not moving. So in fact, there are many forces that are acting on this table, right? Its own weight is acting downwards, okay? But it is not moving because it is in the state of equilibrium. Now, if I push this table a little bit, what will happen to it? It will move a little bit and then again come to equilibrium. So the property of any system to come back to equilibrium when you perturb it slightly is known as stability. So more the number of legs, the stability will be more. That's why an insect is almost instantaneously walking because it doesn't need to learn to stand. A deer will take little bit more time to stand because it has to train its muscles, right? Otherwise, 4 legs are enough for it to stand just like that. But muscles are weak, so muscles need to be trained. Humans take more time because they are bipeds, only 2 legs, so more time to learn stability. Okay? But it's not only the stability, there is another aspect also there. If it was only about stability, then we would make all robots having 6 legs or more number of legs. But sometimes we prefer to make robots of 2 legs also. Why? So let me make you think about it a little bit. Have you seen gymnastics? Gymnastics performed by humans? Yes? There is a Predunova vault, right? So do you think that these gymnastics could be performed by a dog? Difficult, right? Difficult. By insect, much more difficult. So stability wise, insect is much better, quadruped is little bit less better, humans are the worst. But from maneuverability point of view, maneuverability means moving from one equilibrium to another equilibrium very quickly. Fewer number of legs is better. With 2 legs, we can do many interesting things actually, right? Provided we train ourselves. People can do somersaults, right? People can do handstand and all those things they can do. On the other hand, this is not possible with more number of legs. So if we are designing a machine, robot for a particular application, then we'll have to have a combination of stability and maneuverability, depending upon what application we are putting it into. And this mixture is again an aspect of intelligence. This is again an aspect of intelligence, which has to be built into the system. Okay? So different types of leg structures you can see. Here you can see cheetah, which is a quadruped. There are powerful muscles which are moving these legs, and by means of that it can perform very complex motions, like catching a prey. On the other hand, there are very simple forms of legs also, like this caterpillar. So this caterpillar leg is very simple. It can simply go up and down, right? And the body is stretching and contracting, right? And based upon that it is moving. So there are no muscles involved here. There are no muscles involved here. The other category is centipede. So centipede, if you see, there are many legs. Each leg is performing simple operation, but when you take all the legs together, the whole body is performing pretty complex movement. So on a robot, if we want to build it, we can have these type of joints. You can have these revolute joints connected back to back, or you can have slotted joints which are shown on the right hand side. So now let me show you some examples of different types of legged robots. You know, you have seen how in biology these these creatures move with legs. If we look at single-legged locomotion, do you know which creature performs hopping motion like this? Yes? Kangaroo, right? Kangaroo. Or even small children, you know, they join their leg and they hop around, right? So, one of the advantage of these hopping locomotion is that it can hop over long distances also, right? See, for example, if we have a robot with 2 legs, so its motion will be limited by the size of the obstacle. Like, you know, if the 2 legs are stretched, there is a limit to which they can be stretched. Whereas with hopping, you can jump over, right? Say, you may remember that when there is a lot of rain and you have water puddles around, right? What do? You jump over them, right? You cannot cross them just by lifting your leg and putting it on the other side. But by jumping, you can jump around. So this is an example of hopping robot developed at MIT. So this is the mechanism, you know. Here you can see that this part is rotating and there is this elastic component. So when this rotates, this elastic component gets stretched and energy gets stored. And at the extreme it is released, and because of this release there is this hopping motion. This is an example of a biped. This is you can see the Atlas robot developed by Boston Dynamics. You can see how well it can perform different types of complex motions, like, you know, on different inclined surfaces. It can do somersaults. It will be able to jump. So what you can observe that in single-legged locomotion there was not much of a variety. It was just able to hop around. But here lots of variety is possible because of 2 legs. Okay, because of 2 legs. See, so with suitable training, it can even perform these complex motions that not many humans can also not perform actually, right? Then multi-legged locomotion. So multi-legged locomotion, you can see this 6-legged robot which can move on different types of obstacles. So this is based on insect like a cockroach. And then let's look at wheel locomotion. There are different types of wheels actually. You know, there is standard wheel that you see on a automobile car, right? So which is on the leftmost case. The center one is known as a caster wheel. Where do you see this caster wheel? Yeah, in trolleys, chairs, right? And then the third one is ball wheel. Okay, so in standard wheel, the degree of freedom is only 2. Whereas or even in caster wheel, whereas in ball wheel there are 3 degrees of freedom possible. The difference between this standard wheel and caster wheel is that the degree of the rotation about the vertical axis is at the point of contact in the standard wheel, whereas in the case of caster wheel it is slightly offset. You know, it is away from the point of contact, which gives it some amount of flexibility. And then there is something called as mechanism wheel. So this mechanism wheel is like standard wheel, but it has these mechanism on its periphery which allows lateral motion. You know, the standard wheel, an automobile car for example, you know, it can only move forward. It cannot move sideways. It cannot move sideways, right? in order to move sideways, you have to do steering and lots of complex maneuvers. But in the case of mechanism wheel, by putting these mechanism on the periphery, we can perform lots of sideways motion also, as you can see in this example. So say if you are developing a robot which has to move sideways also, then you can think of using mechanism wheels. So this type of capability of moving in any direction is known as omnidirectionality. Omni means all, right? All. And omnidirectional means it can move in all the different directions. Now there are different types of wheel arrangement needed. So in general, you know, if we have two wheels, and the total center of mass is below the axle, then actually it will be statically stable, means it will not fall down anywhere. Okay, but other than that, so you know, this is one example of two-wheeled robot which is statically stable. It is called a Psi robot, CYE Psi robot. Different types of wheel arrangements are possible, you know. So you can see these different wheel arrangements which can perform motion in omnidirectional way, as it is shown in this bottom figure, or we can have these which is like a rickshaw, right? This is a rickshaw. This is a bicycle type of wheel configuration. This is a Segway kind of wheel configuration, and so on and so forth. So, for static stability, 3 wheels are necessary because at least 3 points of contact are needed. If there are 4 or more wheels, then there is additional stability. If we use bigger wheels, then the torque capacity will be more. See, you might have seen those motorbikes which can perform stunts. They have bigger wheels. Right, they can climb on stairs, and you know, all those kind of things can be done because they have higher torque capacity. On the other hand, if you look at a scooty, right? So it has smaller wheel, so you cannot perform lots of stunts with it because it has lesser torque. So depending upon what you need, you can choose the type of wheels. So if we look at legged locomotion and if we look at wheel locomotion, let's try to compare. You know, if you look at legged locomotion, the motion is always discontinuous, because see, like if I'm walking, right, if you pay attention, walking motion is always moving between motion and state of rest, right? So every time I put my foot on the ground, my motion stops, and then again motion starts. So there is an acceleration and deceleration happening. On the other hand, if you look at a wheeled vehicle, it will continuously move. So whenever there is an acceleration and deceleration, there is loss of energy, right? Because every time I put my foot, I am wasting some energy in stopping. And that is impossible to stop because that is how walking happens. So legged locomotion is energetically inefficient, whereas wheeled locomotion is energetically more efficient. It is continuous. However, then you might think that then why not be always wheeled locomotion? Because wheeled locomotion is energetically good. And why not nature has evolved wheeled locomotion? Why we have walking all over the places? See, the thing is that with wheels, the terrain traversability is less. Means with wheels, you know that wheels get stuck on sand. Wheels get stuck on mud. Wheels cannot climb higher terrains. Legs can actually move on soft terrain like sand. Legs can actually move on rocky terrain. So, you know, engineering is all about trade-offs. You will always, when you choose one solution, it will give you some advantages, but then at the same time it will also give you some disadvantages. So you will have to always manage these things based upon your requirements. So here, what is the trade-off? Legs give you better energy, worse energy efficiency, but give you better terrain traversability. Wheels give you better energy efficiency, but poor terrain traversability. So how about bringing these two things together to get a trade-off? So if we combine legs and wheels together, then what happens? Then what happens is called as hybrid locomotion. So here what is done is that at the end of the legs, wheels are attached. So these type of vehicles are also called as rovers, like Mars rover, for example, right? So here you can see that because of these wheels attached on the legs, its terrain traversability has improved. With wheels it is impossible to climb on such a tall terrain, right? But with this kind of configuration it can. And that's why, in field robotic scenarios, like for example Mars rover, we use rovers, we use hybrid locomotion, we don't use wheels, because we don't know what kind of terrain will be there. There may be sand, there may be rough terrain, there may be whatever, right? So there we design rovers. Then you might think, or I will ask you this question, that why don't we use this excellent locomotion for our road vehicles? What do you think? Because it can climb on anything, so why don't we use it for our transportation? For our transportation we use wheel locomotion, right? So what do you think, why? Any thoughts?
Economically not that sustainable.
Sorry?
Economically.
Very good, very nice. Because these are very complex designs, right? You have legs, you have wheels, you are attaching them together. So the design is much more complex and it is more expensive. So you would rather use it in applications like space applications, where you don't care as much about small expenditures like this. But in road vehicles, if you start doing it, your cars will, costs will increase by a factor of 10 actually. Then there is something like, we have seen legged locomotion, we have seen wheel locomotion. In nature, there is one more type of locomotion which is crawling, snakes, right? So even robots are built based upon snake locomotion. The way snakes move is by using a vertebrate structure. So snake's body, if you broadly, if you want to think about it, is made up of many vertebra, and each vertebra is a ball and socket joint. There is a ball and there is a socket, and this ball moves in the socket, and these things are put back to back, and then there is a skin around it, and that's how snakes move, right? That's, very, very roughly speaking, that's how snake locomotion works. Now, you see, there are different ways in which snake body can move. So one movement is known as lateral undulation. You can see here. Here, an S-type or S-shaped wave moves from head to tail, and by means of that, the snake is moving forward. Okay? This is one type of locomotion, one type of snake locomotion. There is another type of snake locomotion which is shown over here. This is known as concertina. You see the difference between these two? I'll ask you one question. In which case, which is based upon our previous discussion, in which case between lateral undulation and concertina, the bottom one, the energy efficiency will be better? First one. Lateral undulation, right? Very good. Why? Because it is continuous, right? It is continuous. So, so that's a good thing, right? That's a good thing about lateral undulation, that energy efficiency is better. But what about the bad thing? You see, the area required, the width required for locomotion is much more in lateral undulation than in concertina. In concertina, it can actually take very little space. It is like, a soldier walking on elbows. Have you seen that motion? That's also called as concertina, right? So that is usually done for stealthy. Stealthy means hidden. छुप कर जब जाते हैं तो. So this is snakes usually do it either to protect itself from the predators, or it usually does it when there is less space. See, in lateral undulation it is moving around like a king, right? So anybody can catch it. So it usually does it when it is free of any danger, right? So less energy, it will spend less energy and move easily. But when life is in threat, or if it has to catch something for eating, then it would rather prefer concertina, right? So it's not that the snake perform only these two type of locomotion. There are other type of locomotions also, like this linear motion, rectilinear motion. So in rectilinear motion, the snake in a sense stretches its body, okay? And then there is a covering on the underneath of the snake, underbelly of the snake, which sticks on the ground, and then thereby it moves straight, right? In fact, there is a very interesting thing about snakes, that if you take a snake but don't try it with live snake, okay? So if you take your hand from sideways, right? Like let us say this is the snake body, right? If I move my hand like this, okay, and if I move my hand like this, in which case it will be rough. Will it be same or will it be different? First question. It is different, okay? In this case it is different, or in this case it is more, or in this case it is more. Roughness. Roughness is more in which case? Actually the first case. This is much rough. Okay? The reason this type of difference in friction is known as anisotropic friction. Anisotropic friction. You have heard this word isotropy, right? Isotropy means same. So anisotropy means different. So actually snake's body has different friction in different directions. Longitudinally it is less, it is smooth. Laterally it is less. And because of that it can actually perform locomotion. Not only that, if you move your hand from snake's head to tail and from tail to head, the smoothness is different, the roughness is different. Because of which it can move forward. When it sticks itself on the ground, it is not slipping backward. It is always slipping forward. So friction is very, very critical in snake locomotion. Then this is one last type of snake locomotion called as side winding. So here you can see that snake is moving sideways. This is used by snakes to move on soft terrains like sand. So this is an example of rattlesnake. Alright, so many different types of snake locomotions we have seen. Now let's see how they are incorporated in robots. So first thing that you might have observed about snakes is that their body is always long, right? Body is long. And second thing that you must have observed that different parts of the body are performing similar motion, right? It's like this, right? If you just take a small piece of the snake body, it will basically move like this, right? So say if on a plane something needs to move, how many degrees of freedom it should have? Like how many minimum number of variables are needed to describe anything on a plane? Say if I talk about a point, just one point, think about just one point on this board, right? On this board I put a point. How many minimum number of variables are needed to describe that point? Yeah? 2, right? So 2 degrees of freedom. If I have 2 points, then how many variables are needed? 2 for first point, 2 for second point. But now suppose I connect these 2 points. Like, I take a pencil, for example. There is a tip of the pencil, there is a top of the pencil. So now if that pencil is stuck on this wall, I stick it with a scotch tape. Now how many variables are needed to define it? Well, this is a trick question because there are 2 points, right? 2 endpoints. So 4 variables. But there is one constraint between these 2 points. Like these 2 points cannot move in any way. The distance between these 2 points must be fixed. So it is 4 minus 1, 3. And what are those 3? The x coordinate, the y coordinate, and the orientation. How it is tilted. Okay. So on a plane, if we want to describe a motion, we will need 3 different variables, minimum. But in a snake, if you see, there are more than 3. There are more number of controls because there are large number of body, you can say, segments, and each segment is performing 1 degree of freedom. So if you add all of them, it is more than 3. This thing is known as redundancy. Suppose I have a light switch over there and light bulb over there, and I have a switch over here. One switch. If I turn it off, the light turns off. Turn it on, light turns on. But say if there are 2 switches, one here on the front, one in the back. Both are performing same operation, turning the light on and off. So now we have redundancy of switches. 2 switches are performing same things. So here there are many different movements than 3. So that's why there is redundancy in motion. In fact, that redundancy is very high, therefore we call it as hyper-redundancy. Okay? So this type of design of a snake robot will be called as a hyper-redundant design. What is the advantage of having 2 switches to turn on a light? If one fails, another will work. Yes? Even if one fails, one switch is bad, another switch will work. You can operate this light from different places if the room is big, right? Likewise, if 3 degrees of freedom have to be controlled, but you may want to arrive at that 3 degree of freedom in many different ways. So for that, redundancy may be needed, or one of the joint fails, one of the joint gets hurt. Still, the snake will be able to move, right? So that is the overall design philosophy behind developing snake-based robots. So in snake-based robots, the entire robot is made using different modules. So here you can see one module. This one module, if you see, it has 2 links connected by a joint, and they are performing 1 degree of freedom motion. Now think about this one module connected back to back. That's what is a snake robot. If you want to design your snake robot, first you have to make this module. Take a motor, take one link over here, another link over here, and then you put a controller on it which performs some kind of sinusoidal motion. And then you connect them back to back. And what you will get will be a snake robot. So these are different types of snake robots. This is one snake robot at the top right. You can see what type of locomotion it is performing. You just now saw few minutes ago. Lateral undulation, right? There are so many different types of snake robots. I have listed some of them here. This is another type of snake robot on the bottom right. What type of locomotion is this? Rectilinear. Very good. Very nice. So then these snake robots can also be made what is called as reconfigurable robots. What is a reconfigurable robot? See, if you have a long snake robot and you break it down into small pieces, and these small pieces combine themselves in a different way or reconfigure them, then that is known as a reconfigurable robot. So here you can see that this one single robot breaks itself down and makes itself as a legged robot. Okay. So again, depending upon the mission. So for example, let us say there is a snake robot moving in this room, right? And it has to climb all the way up to that door. So there are these stairs. Now snake robot will not be able to climb the stairs. Yes, it won't be able to climb the stairs. If you make self-configurable robot, the snake will break itself into many pieces, combine itself into a legged robot, and then with legged robot it can climb up. Again, there is an intelligence needed for this, right? That's also where artificial intelligence will be required. Okay. So you might also wonder that why do we need snake robots actually? Like, what is the application? Is it only for fun, or there is some application also? In a disaster situation like an earthquake, there can be lots of debris and victims may be stuck in that. And the rescue effort has to be very quick and focused, because debris will always be huge. A building, when it falls, it's not localized in small place. So first of all, the victim has to be found out in a way that is quick and that is not harmful for the victim. Say for example, if you want to find the victim out, you just start moving around debris, you may kill the victim in the process, right? So these snake robots can be very, very helpful in that kind of application, where they can go into very narrow places, and if there is a camera in front of that, or if there is some carbon dioxide sensor, then it can detect the presence of victims and relay it back to the rescue person. So rescue person can actually go and save that person quickly. Okay. Another application could be inspection of pipe-like machineries. Here you can see that in a pipe, the snake type of robot can go in and detect cracks or any kind of flaws. Like these huge machines, like turbines, they need complete decommissioning for routine checkups. Okay. As opposed to that, if there are these snake robots that can be sent into running machine, then a lot of time can be saved. So snake robots can be very, very helpful in applications like rescue, like pipe inspection, like large machinery inspection, and so on and so forth. So actually there is a lot of material. Worm locomotion can be, based on two anchors. You might have seen these leeches that can stretch its body and anchor themselves, and then, the longer it stretches its body, the longer stride it can take actually, right? So how can we incorporate such things in robots? Caterpillars can perform what is called as caterpillar tree anchor crawling, right? I had shown you one video in the beginning. And peristalsis is one where, like earthworms, if you have observed earthworms have many segments in their body, and segments can be stretched and contracted in a wave-like fashion. And by means of this contraction and stretching, cyclical contraction and stretching, it can move forward. So this type of motion is known as peristalsis. Actually, in our body also, there is a place where peristalsis works, right? In our intestine. So for sending the food down, there is a peristaltic movement that happens in the intestine, and by means of that the food actually is pushed down. So there are certain robots that I'll show you. These robots are designed based upon earthworms. So there is a motor at the end. You can see at the rear end of the robot, you can see the motor which is rotating, and the mechanism is transmitting the rotary motion to contraction and stretching, or what is also called, I said as peristalsis, and by means of that it actually moves forward. This is another type of peristaltic locomotion, as you can see. Here the locomotion is done using not using motors, so you can see how robust it is. Even with hammer, when it is beaten, this robot can move. So these type of robots are very slow, and they have very niche application. But they are very important from the point of view of study in robotics. This is a caterpillar inspired robot. This is a 3-anchor crawling. You see there are 3 anchors, one in the rear, one in the front, and one in the middle. And each of these links move with the help of motors, right? So by cyclical motion of these motors, this 3-anchor crawling can be realized. This is one robot which is developed in our own lab. So this is again 3-anchor, multiple anchor crawling actually. Now aquatic locomotion. So there are different types of fishes from which we can learn how to build robots. Okay, so based upon the way the body is moved, the fishes can be classified into anguilliform and carangiform. Let me explain you what that is. See, fishes can move their bodies by, they can generate propulsion by means of moving their tail fins, or they can move their paired fins, or they can use some other type of locomotion which I'll explain. If they are using their tail fins, the whole body can be used as a tail, like in this case. Here you can see the entire body is undulated, and by means of that force is produced which is making the fish to go forward. This is known as anguilliform locomotion. Anguilliform locomotion. These are some robots that are designed based upon anguilliform locomotion. This is another type of fish locomotion where only part of the body, not the whole body, but part of the body is undulated. This is known as carangiform locomotion. So carangiform fishes, robots are like this. Here you can see the front part of the robot is where motor, controller, batteries are there, and the rear part is like a tail fin which oscillates, and by means of that locomotion is performed. So these are different examples. There are examples where fishes only move oscillate their tail fins, not even undulate. So like in this case of box fish. So here you can see, similar to box fish, real box fish, this robot has a tail fin over here which oscillates, and by means of that locomotion is performed. This is another type of locomotion where side fins are used, what are also called as median and paired fins. So these paired fins you can see on the side, these red things. So in this robot, these red fins are moved. By controlling the difference of oscillation of these red fins, the fish robot can move forward or turn left or right. This is known as gymnotiform locomotion where anal fin is used. Anal fin runs from head to tail, and in robotic world, this anal fin is implemented like this. This is rajiform where both undulation and oscillation is combined, as you can see here, and in robotic world it is implemented like this. So these are different types of fish locomotions based on fin movement. Now you know that if you look at whales are actually mammals. They are not exactly, they don't fall into the category of fishes, but these whales are huge, right? And they have to come to the surface of water in order to breathe. So they keep doing up and down. How do you think they keep going up and down? Are they always using their tail fins to go down? No. They use buoyancy. They use buoyancy because see, if they use their tail fins to go down every now and then, they will have to spend a lot of energy, right? They will have to spend a lot of energy because the bodies are big. There is a lot of drag force. So the way the buoyancy works is that the total volume of water displaced by the fish body, the weight of that water is the upward force, right? And that is known as buoyancy force. And then the weight of the fish is downward force. So if these two forces balance each other, then the robot will, or the fish will swim, right? Float rather. So that is implemented using these kind of ballast type of mechanism where water is sucked into the body of the fish, right? And then that water, when sucked into the body of fish, it increases its mass and accordingly the weight. And because of that increased weight, the buoyancy reduces and it can go down. And when it has to go up, then it throws the water out and thereby its weight reduces, buoyancy increases and it will float up. This is actually done by, this is actually used by sperm whales. So the sperm whales have an organ called as spermaceti organ, based on which the name sperm whale is there. So in this spermaceti organ, which is in the head of the whale, there is a material which is like wax. Okay, so when the whale has to float up, what it does is it rushes all the blood to its head, and because of the warm blood, that wax-like material liquefies, and because of that liquefaction, the volume increases, and because of that volume increase and no loss of mass, it actually floats up without spending much of energy. And when it has to go down, all it does is takes the blood back into the body. Because of the surrounding cold water, the wax solidifies, the volume contracts, and because of that it again sinks down. So that's how the the biological world works. And this is implemented in many robots also, which we will see even in the afternoon session. Jet propulsion is another method by which these fishes move. So what they do is they suck water in and then they produce a jet, and because with that jet they can actually perform locomotion. So these are usually seen in jellyfishes. So these are some robots based on jellyfish type of locomotion. Here the robot is creating a jet of water and thereby it is performing locomotion. Here you can see on the bottom also. So so getting into little bit of basics of how these actually so many excellent things are made, right? So basically, we have this mechanism which allows for transformation of motion from one form to another form, right? So these mechanisms are made up of links and joints. Joints could be prismatic, where the motion, linear motion between two links is permitted, like in this case that you see here. Or rotary motion can be permitted, like in this case. So these are known as revolute joints. Degree of freedom is the number of independent motions that can be performed. There are different types of mechanisms. I'll show you some configurations here. This is known as Cartesian configuration. So in Cartesian configuration, you can see that there are 3 prismatic joints. So these are also known as PPP configuration. PPP configuration. Here there is a revolute joint and 2 prismatic joints. So these are known as RPP configuration. This is RP configuration. There is a revolute joint, another revolute joint, and then a prismatic joint. This is a SCARA configuration, articulated configuration, and so on and so forth, different types. This is a 3 degree of freedom wrist, which can be incorporated into robot. So here, like for example, in human wrist, this motion is known as pitch. This is known as roll, and this is known as yaw. And then there are different types of end effectors or tools that can be put on the robot. So here you can see these magnetic grippers. So you see this electromagnet, when we pass current through this, it becomes magnet, and then because of that magnetic field, this object will be gripped. So these are known as magnetic grippers. Or there can be mechanical grippers, where because of the mechanical force, the objects could be gripped. So various tools can be attached to the robots, like welding guns, spray paint guns, screwdrivers, heating torch, to perform different operations. Different types of actuators can be used in robots, like electrical motors or pneumatic cylinders. You know what are pneumatic cylinders? There are these cylinders with piston. When pressurized air is sent on one side, one end of the cylinder, the piston moves, and by means of that, robot is actuated. And when this, instead of air we use liquid, then we say that these are hydraulic actuators. So a typical task in robotics would be to take an object from one place and take it to another place, right? And how we actually do it, by performing first the modeling of the motion. So modeling means that what kind of joint angles or what kind of joint movements we give, based upon which the robot performs what kind of overall motion. So that is known as forward kinematics. Here you can see that you see when each of the joint is rotated by a certain angle, the end of the tool of the robot, which is at the end, it moves in the space, right? So the relationship between the movement of the tool and the movement of each of the joint is known as forward kinematics. Okay? So for example, in my arm, my fingers will move based upon how I move these joints, right? If I, let us say, set my shoulder joint angle to 30 degrees, elbow joint angle to say 90 degrees, then where will this be with respect to my shoulder? This relationship is known as forward kinematics. And inverse kinematics is the determination of the joint angles that are needed to take this end effector or the tool to a particular place, right? So suppose I want my fingers to reach to a particular object, so I have to pick them. So for that, for the finger to reach to that location, what should be the joint angles? This is known as inverse kinematics. So first we solve for forward kinematics, and then we solve for the inverse kinematics. I'll skip some of the math from here. Okay, so now let's look at robot path planning using AI-based search techniques. So now that you have gotten some introduction to how these robots operate and how these robots are made, and you know what kind of inputs are needed to make these robots move around, Then let us see how we can apply artificial intelligence based search in this. Okay. So consider this scenario where the robot has to go from this start location to the goal location, right, which is mentioned on this slide. And then there are various obstacles in the scene, which are shown by those red colored things. So at no point the robot can hit the obstacles. The penalty is very high. The robot may get destroyed, right? So the robot has to find a path which is free of obstacles. So this is a problem of path planning, robot path planning. This is a very important problem in robotics, where AI is used, artificial intelligence is used. So here, what are the things that are known? Well, we should know what is the pose of the robot, where the robot is located in the beginning. We should know the obstacle locations, and we should know the robot capabilities, that how the robot can move actually. And based upon that, we need to determine a collision-free path. So now this problem, this problem where we know where the robot is located, where it has to go, and where the obstacles are located, can be solved using path planning algorithms. Now, what is an algorithm? Most of you are from first year class, so you might have seen different types of sorting algorithms, for example, right? Yes? In programming, you might have implemented sorting, bubble sort, and those type of algorithms. So what do we do in an algorithm? We have an input and we convert that input to some output, desired output, that satisfies certain requirements, right? For example, let us take an example of baking a cake. Baking a cake or making a roti, for example. Let us say making a roti. So in order to make a roti, what do you need? You need flour, not the flour, sungne wala, atta wala flour, right? Then you need water, right? What else do you need? You need heat, source of heat on which you can cook it. You need something to flatten, right? So these are all inputs. Now, you take these inputs. Now, suppose if I tell you that first you turn on the, whatever cooktop you are using, say you are using any kind of heated plate, right? You first turn it on, then you turn it off. After that, you take some atta, okay, and then you roll it, and then you put water into it. Will you end up making a roti? What do you say? No, right? You will end up making a mess, not a roti, right? You will end up making a mess. Well, the steps that I mentioned, all these steps where you first turn on the heat, then turn it off, and then you put water into the, you just roll the atta and then you put the water. This is also an algorithm, although a very bad algorithm, which cannot produce the desired output. But it is an algorithm, right? It is an algorithm. In fact, any sequence of steps is called as an algorithm. But there are good algorithms and there are bad algorithms. There are useful algorithms and useless algorithms. In the case of motion planning or path planning, what is the objective? Here objective is not to come up with a roti, right? Here the objective is to come up with a, yes, path. What kind of path? An obstacle-free path, collision-free path, right? So, and here instead of atta and water and heat, the inputs are robot's location, goal location, obstacles location, right? And robot's capabilities. So the algorithm should satisfy, the algorithm that will solve this problem should satisfy certain properties. What properties should it satisfy? It should be what is called as completeness. What is a complete algorithm? A complete algorithm is that which will return solution if the solution exists, and which will return failure if the solution doesn't exist. Okay? A complete algorithm is one that will return solution if the solution is there. If the solution is not there, then it should return failure. It may sound obvious to you, but actually it is not that obvious. Because there can be algorithms which can return you solution if the solution exists, but if the solution doesn't exist, then it may run forever. Okay? In that case, those algorithms are called as semi-complete algorithms. Semi-complete algorithms. But if there is an algorithm which doesn't return the path, even if the path exists, even if the solution exists, those are called as not complete algorithms or incomplete algorithms. Okay? So completeness is a very, very important aspect in path planning algorithms. So let us see how do we solve the problem, and then we'll come back to this point of completeness. Why we discuss completeness, we'll come to that. So let us say there is a world, like for example this room. From the top you are looking at it, and there are some obstacles which are represented using these circles, right? Red circles. There is a robot that has to go from a start point to an end point. So what we can do to solve this problem is to first represent this world so that we can store it in a computer. Because eventually you have to program it on a computer and solve it, right? So how do we store it on a computer? What we can do, we throw a grid, like you have seen those tiles. So say in a room there are many things like table, chair, people and all that. And the room has tiles, okay, rectangular tiles. So every tile you give some name, some number, right? Like tile number 1, tile number 2, tile number 3 and so on and so forth. Like this, the middle figure. In the middle figure you can see there are tiles. Some tiles are free, means there are no obstacles on them. And some tiles have obstacle on them, yes? So on the third figure you can see that the tiles which have even partially obstacles, we make them as completely occupied tiles. Means robot should not step on red tiles. It should only step on white tiles. And we have to come up with a sequence of these tiles such that the robot follows shortest path and doesn't go through any of the red tiles. Okay? Now if we think about the room or about the world or about the space in the form of tiles, then it becomes easy to store on a computer, right? Because every tile has an address and we are storing that in a computer. This is known as a graph representation. Okay? Graph. So you might have plotted some graphs in your physics lab. I'm not talking about that graph. In computer science, there is a structure known as graph data structure, right? So how does it work? See, I told you that we need to know where the robot is located, and we need to know also how the robot moves. So on the bottom side, if you see bottom left, there is a figure which shows at the center the robot is located, and the robot can move to the east, shown by E. It can move to the north, shown by N. It can move to the west, shown by W, and so on and so forth, right? So it can also move northeast, for example, which is in the middle of north and east, right? So there are 8 possible actions that the robot can perform. Now in this world, each tile is given a number, like tile number 1, tile number 2, tile number 3 and so on and so forth. We can store it on a computer in the form of a graph, where we store not only the tile location and whether it is available or not, available in the sense of whether there are obstacles or not, but we also store which other tiles they are connected to. So if you program already, then you know of say structure like struct in C, right? Or class. So in a class class, you can make some variables, right? You can make some variables which represent the reference to another object of that class. Okay? So the class is that of, the class name will be node, right? And node will have members like, X, Y, which represents its location. It will also have reference to object of the same class, which is another node, right? So you have these different nodes like 1, 2, 3 representing different types, and then their interconnectivity. Now once you have this structure or graph, the whole task is to search for path on this graph using what is called as graph search techniques, which is a well-known AI search technique, right? Graph search technique. You will see some of the graph search techniques today. So let's look at one example here. Let us say there is a self-driving car, which is also a robot, by the way, right? A self-driving car, which has to go from a city of Arad to Bucharest, and there is a map given to you, right? I mean, on the computer, on the computer of the vehicle or self-driving car, all this map is stored. Now you see that distance between different cities are stored. Like between Arad and Zerin, there is a distance of 75, and so on and so forth. So now the question is, how do you find the shortest path between Arad and Bucharest? Right? How do you search? Node data structure that I was telling you about, right? So node will have a state, parent node, action, path, cost, depth, and so on and so forth. And we search on this structure. There are different types of functions that are, that run on this graph structure, called as make queue. So if you have multiple nodes, you give it into the make queue function, and each node will be added into that queue. Queue is like a sequence of nodes. It's like, if you are standing in a queue for getting some gift, right? So there are 5 people standing in the queue. So I will first give the gift to the first person. Then the first person will leave, and then the second person will come, right? So the order of giving the gift will be in the order in which they are standing, right? This is known as a queue. So in order to form the queue, this make queue function is used. Then empty queue will return if the queue is empty or not. It will return a Boolean flag, right? So whether the queue is empty or not. The function first will return the first member in the queue, okay? And remove first will remove the first member in the queue. And insert will insert one node into the queue, right? And so on and so forth. So the basic idea is this, if we have to find a path from Arad to Bucharest, we first begin with Arad. We follow what is called as tree search. So we begin with Arad, and then we look at all the children nodes or all the connected nodes to Arad, right? So in this graph, if you see Zerin, Sibiu, and Timisoara, these 3 cities are connected to Arad, right? So in the tree search, we add these 3. Then next is we explore Sibiu, and we expand that, right? And we keep doing it. We keep doing it until we expand the node corresponding to Bucharest. And then we look at the parent node of that and parent node of that, and that way we reach to the initial node, and the sequence of nodes that we get in the queue will be the path. Okay, that's the basic idea, roughly, right? That's the basic idea. And the algorithm is shown on the left hand side for that. Now, I told you about the messy algorithm for making roti, right? Which will not make roti, but which will make a mess. So how do we determine whether our algorithm will end up making mess or end up giving us path? So first we should check whether this algorithm is complete or not. Meaning that If the path exists, then it should return path. If the path doesn't exist, it should return failure. Okay, that aspect should be checked. The second thing is optimality. Optimality we discussed in the beginning of our lecture today, that whatever cost metric, whatever is of importance, that is maximized or that is minimized or not. Okay? Then complexity. Complexity is another thing. All the computer science guys, you will have to study a lot in the next coming years. Complexity means, complexity is of two types, right? Time complexity and space complexity. Time complexity means how much time, roughly it means how much time that algorithm will run, will take to run, right? So in other words, how many computational steps are there? You add all of them together, and that is known as time complexity. Space complexity means how much space is needed, how much memory is needed to run this algorithm. So if an algorithm has high space complexity, then it will require more RAM. Okay? If an algorithm has high time complexity, then it will require more processor clock speed. Okay? So, we will look at a couple of algorithms today. So I'll look at graph search algorithms only for the purpose of today's discussion, which forms the basis of, artificial intelligence. Forms the basis of artificial intelligence. There are many things in AI. We cannot cover everything in one session, but search is one very important thing. So let us look at uninformed search. Uninformed search, also known as blind search. Algorithms that will look at depth first and breadth first search, sometimes known as DFS and BFS. So first of all, let us see why they are called uninformed search algorithms. Uninformed, like the name suggests, there is some information which is missing here, right? Uninformed means some information is not given, also called as blind search. So for any search, say for example, let us say I want to search for a water bottle in this room, right? I want to search for a water bottle. I need some information for sure, right? I may have some lack of information, but some information I need. So for example, say, let us say you blindfold me, okay? You blindfold me and then I start searching for water bottles. So I will know if I touch the water bottle that it is actually a water bottle, right? And I will also know how to move in this room. And then if you put a blindfold on me, then I will eventually, keep looking for the water bottle, and eventually I'll keep touching everything, and finally I'll find a bottle. Okay? What I will not know with my blindfold on is how close I have come to the bottom. Every time I move, I will only know that how I have moved from my initial place to the next place. But I will not know how close I have come to the bottom. So this may mean that I'll have to search a lot basically, right? So in the case of uninformed search algorithms, the closeness to the goal is not known. That information is missing. But whether a given node is goal node or not, that information is known. And what are the children nodes, or what are the connected nodes or neighboring nodes, these are known. So let's look at this example here. There are 6 snapshots of search. 6 snapshots. The top left, if you see, now you see the red colored things are obstacles, right? So on the top left, the scene is shown, and the second one on the top row, you will see that the top left node, yellow node, is the robot starting location. Okay, it's the robot starting location. Now, in order to search, first all the neighboring nodes have to be listed, right? So we know the robot's capability, means how the robot can move. It can go to east, it can go to the south, west, north, and so on and so forth. So obviously north and west, these options are not possible because world is not there, right? World is not there. as far as east and south is concerned, expansion is possible. So we expand that. Now the neighboring nodes will have depth of 1. The neighboring nodes will have depth of 1 because initially the depth is 0 and then after that the depth is 1. Now next we search for the nodes that have the least depth. In breadth first search algorithm, we always expand nodes that have the least depth, that have the smallest depth. So obviously here all the two nodes have same depth. So we can arbitrarily choose, we can arbitrarily break the tie. And let us say we take the bottom one and we expand. So now we have 3 nodes that are unexpanded. And the top one has, if you see, bottom right figure. In that one node which is to be expanded has depth of 1 and other 2 have depth of 2. So we choose the node with depth of 1 and we expand that. Because in breadth first search we always expand the node with the least depth. And we continue like this. So this type of search strategy is known as breadth first search, BFS. So a BFS algorithm is exactly same as tree search algorithm, but here we have to use the queue. We have to use the queue which is first in, first out. Okay? First in, first out queue means that the node that goes into the queue, that comes out first. Okay? Likewise, so by the way, the complexity of breadth first search algorithm is, if the number of nodes that are expanded is B, like B can be 2 for a binary tree. A binary tree is one where 2 nodes are expanded, right? So the complexity of this algorithm is actually of the order of b to the power d plus 1, where d is the depth of the tree. So basically this is a very bad algorithm in that sense, because if you increase the branching factor, meaning the number of branches that needs to be explored at every step, then the algorithm will take exponentially high time and exponentially high memory space, right? So in fact, in this calculation you can see that just for exploring a tree of depth up to 14, calculations of up to 3,500 years have to be done. So obviously breadth first search in its original form cannot be used for very complex searches, but then why are we looking at it? This is one of the basic algorithms which if you understand, then you can understand more complex algorithms later on, right? So even if you cannot understand breadth first search completely today, if you know some of these terms and you go back and check, there are some excellent books on this topic, like the one by Russell and Norvik's book, Modern Approach to Artificial Intelligence. Then you can easily understand it and you can program your robot for search with this. In depth first search algorithm, the strategy is reverse. Here, instead of expanding the node with least depth, we expand always the node of highest depth. Okay, node of highest depth. So in the case of DFS, the same tree search algorithm will work, but here the queue has to be last in, first out. And here the complexity of, the time complexity is same as the breadth first search, but the space complexity, the number of nodes that needs to be stored is less. It will be of the order of depth actually. Alright, and then let's look at A star, which is usually used, in many robotics applications. A star algorithm is used. This is known as informed search. So on top of uninformed search, in uninformed search algorithms, we only had the information about whether a node is goal node or not and what are the neighboring nodes. We have one more information available, which is known as the proximity to the goal. Proximity to the goal, which is in the form of something called as heuristic. So let's see what that is. So a heuristic is a function that returns you the measure of how close a given node is to the goal. So like the function hn here, hn. H is a function when you give n, which is the given node, then it will return a measure of how close the goal is to it, right? And this heuristic should satisfy a property called as admissibility for this A-star algorithm to work. So admissibility is a property which tells you that this function will always return a value which is less than the actual cost, right? Which is less than the actual cost. All right, so I think that's it. I think that's about the artificial intelligence. So anyhow, this morning we covered different types of robots, how robots are made, what are the different components of robot, and then how different types of biological inspirations are used to design a robot, right? And then we also saw one example of how artificial intelligence can be used in path planning. So now in the afternoon session, I will be going through some of the research results from our lab, and we will try to connect it with whatever we saw this morning. So first problem that I will be talking about is underwater exploration. So, more than 70% of Earth's surface is actually covered by water, right? In fact, it turns out that out of that 70% of water, more than 90% is not explored yet properly. There are lots of natural resources like say oil, petroleum, many biological systems, ecosystems, those things exist in this water environment. So it makes sense to explore these environments to obtain or to extract the useful, the useful things out of them. So in order to do that, usually human divers explore these areas, but they find, it's like risking their lives, particularly when we are talking about very deep waters, or we are talking about unexplored regions where we don't know what kind of pathogens or what kind of environmental risks exist. So it makes sense to use robots to explore these areas. But in order to use robots, there are several challenges that have to be mitigated. So, these different places may have narrow regions, there may be pressure, hydrostatic pressure, there may be flow, currents, there may be waves, and obstacles, obviously. So think about this underwater structure where the exploration is needed to find out some defects, to find out some kind of problems in the structure, some kind of problems in the these underwater machineries. So, or you can have an environment where we have these coral reefs, where lots of useful ecosystem exists. So how can we use robots in these environments, right? So the next few slides, I will be talking about how we address the problem of underwater exploration, some aspects of underwater exploration. So one of the crucial aspects of underwater exploration is trajectory planning. You remember the planning problem that I was discussing this morning. So we use anguilliform inspired robot for exploring narrow regions in water. And you remember, if you remember, anguilliform locomotion is one where the whole body is used for performing locomotion, right? So here you see this is an underwater structure, and you see this robot that has to explore this area. There are many narrow regions, flow, and so on and so forth. So let's look at these two scenarios. On the left hand side, you know, we have shown this, shown the top view of the whole environment, right? So the robot has to go from starting location to the goal location. So if you look at the left hand side, the shortest path from the start location to the end location has been shown, right? But it turns out that when flow is present, if you remember, I told you this morning that if flow is present, then going straight means actually you are shifting sideways because of the flow. So say flow is coming from this direction, and if I try to go straight, I will not end up here, but I'll end up here. So in order to end up in a location next to me here, I should actually move like this to compensate, right? So how do we plan so that we can get a path which is like the right side, where we compensate for the influence of flow? So that is one of the objectives of this particular problem. So I had shown you this robot this morning, which we built in our lab. So this robot has 5 links, and it can move around in the water, but the question is that how do we determine the trajectory for this robot so that it doesn't hit the obstacles and it takes into account the flow around itself. So in order to solve this problem, we follow several steps. So in the first step, we develop a model of this robot, a mathematical model of this robot. Secondly, we determine the parameters of this model, and thirdly, we perform the trajectory planning. So in order to make the mathematical model, if you look at the left hand side is the CAD model of the robot. On the right hand side, you see the idealized model of this robot. So it's like a continuous line, right? Like a snake or eel. We divide it into some segments, as you can see. And with respect to each segment, we associate a frame of reference. I'll not get into too much of mathematics here, but we'll show you what sort of math goes into this. And if you are interested, I can send you our research paper, which you can read later on at leisure. So the robot's state is determined by means of the centroid of the robot and its orientation, and it operates in a flow environment with a flow velocity equal, which is shown over there, right? And then there is some drag occurring between the robot and the surrounding environment. So I'll just show you so this is the equation. You know, I'm not going to get into these equations right now, but just showing you that these are the equations that describe the motion of this robot. Now, here, these equations that I have shown you are coded up in MATLAB. okay, in a programming language. And you can see that with these equations, the simulated robot, this is the simulation. Simulation means it is the replication of the reality. How actual robot will move, we determine by using the model. So it behaves in the similar way as the real robot, right? If the flow is present, which is like this, you know, these vertical arrows, then you will see that this robot will, you know, slide, will drift sideways, you know, upwards little bit, because of the interaction between the robot and the flow. So by using these equations, we can actually capture the real behavior of the robot. Okay, so this is the first step towards solving the problem of trajectory planning. So first step is to develop a mathematical model. So if you are designing any robot and you want to, you know, impart intelligence to that robot, the first step will be to develop a mathematical model like what I have shown here, and then simulate it. After we develop the model, the basic problem can be described like this. You know, the robot is initially located at the origin of this frame of reference and it has to go to this goal location. By avoiding these obstacles and at the same time making use of the flow, surrounding flow. So as a first step, we generate the motion primitives. I'll tell you in a moment what are motion primitives. And then we develop a data structure for that, data structure for search, and then finally use the data structure to generate the trajectory. So let's go into each of these steps. Generation of the motion primitives. So you see on the left hand side here, we can see the flow directions. So all these arrows that you see, they show the flow direction. We have discretized it into these many 8 different parts, right? So I should not say part, 8 different directions. So you can imagine that flow can act in any direction, right? So we are assuming that if the flow is acting at 0 degrees or 5 degrees or 10 degrees, then it's almost the same. But if it is at an angle of 45 degrees, it crosses 45 degrees, then the flow changes, the influence changes. So for each of these different flow directions, if you remember that simulation that I had shown you, we can actually run the robot for each of these flows and find out how the robot moves. Okay, how the robot moves. So for each of these 3 actions, on the right hand side if you see, the first, in the middle, the robot is commanded to go straight or left or right. So each of these 3 different motions can behave differently for each of these 8 different flow directions. So in all there will be 24 different cases, right, which are shown over here. You will see, you know, these different directions for straight motion, their behavior is slightly different. So these are all calculated using MATLAB, right? MATLAB simulation that we have developed. So you can see that same straight motion will have different connectivity from the start location. So likewise, you can imagine that for left and for right also we will have another different connectivities. Now, once we have this, you know, so we have the start location and goal location, and the robot moves like this. You know that when the robot moves, it will occupy certain region in the space. So if we make a surrounding polygon, then this is the region in which we don't want any obstacle to be present. Because when the robot takes this action, it will occupy this region, and this if we can ensure that this region doesn't intersect with obstacles, then we can ensure that the robot will also not collide, right? So corresponding to each action, here I've shown straight action, left action and right action. Corresponding to each action there is an envelope. That envelope represents that that action how much space it is occupying. So these are all calculated using the same set of equations and MATLAB simulation that I had shown you, right? So now for all the different flow directions, 8 different flow directions, right? We calculate these different envelopes. These are known as motion primitives. Why motion primitives? These are like atomic actions. We have discretized, we have divided these into building blocks like bricks. When you have to build a building, you make it out of bricks. So these actions are the bricks for making the entire path or entire trajectory. So we join each of these actions and then thereby we can get the overall trajectory. So how do we do it? You see, now from the start location, we have the flow direction available, right? And if we look at these 3 directions, 3 actions, then corresponding to these 3 actions, we can find out the cost to the goal. And the action which has the least cost, we then expand that. If you remember A-star algorithm that we discussed in the morning half. And then we expand that. And this way, if we keep on expanding, we will eventually, lead to one particular action or several actions for which the envelope intersects with the obstacle. And those actions will be rejected. We don't consider those actions. And this way, if we continue, we will eventually be able to make this entire path from the start location to the goal location. So this is the basic approach of algorithm that we have developed. So I'll skip some of the technical details here. Here, what is being shown here, on the left hand side, you can see the nodes, number of nodes expanded using our approach. And on the right hand side, it is the approach based on Euclidean heuristic. So you can see the number of nodes expanded using our approach is much less compared to number of nodes expanded using Euclidean heuristic, which gives us the sense, see, if the number of nodes expanded are less, then the computation time will also be less, right? So our approach is much faster compared to the Euclidean heuristic. And this we tested out for many different scenes. So we created these scenes, we simulated these scenes. So, we created these obstacles in the environment, and corresponding to each of these obstacles, we determined paths. And for each of these cases, we calculated the improvement or speed up between our heuristic and the heuristic, Euclidean heuristic. So what we found out that if we vary the number of obstacles in the scene, which you can see on the horizontal axis in this plot, our approach always gives higher speed up. So that's about the the trajectory planning using A-star based approach and simulation based heuristic that we developed, which we can use to impart autonomy of trajectory planning in the underwater anguilliform inspired robot. Now let us look at another example. Here we have developed shape memory alloy based carangiform fish robot. If you remember, carangiform is that locomotion where not the entire body but only part of the body is used for undulation and creating thrust, right? So here we have used shape memory alloy for designing this robot. So let me explain you how it works. Here you can see the basic design of the fin. So if you see the left figure, it is the CAD model. The blue colored thing is a PET PET, or you can say simple plastic based sheet, right? And at the top the green and the bottom the green layers are basically silicone, or you can say elastomer or rubber type of thing, right? Not rubber but silicone. So at the center of this green thing you can see two wires at the top and at the bottom. These wires are called as shape memory alloy wires. So shape memory alloy wires are, there are many types of shape memory alloy wires. We have used what is called as nickel titanium alloy. So these wires have very special property. Okay. So what is that property? You see, if you take this wire, if you bend it, you know, it will be very springy. Very springy. This property is known as hyperelasticity. Now, if you keep this wire into furnace for half an hour at about 600 degrees C, the property changes. From springy, it becomes really malleable. You know, you can deform it. Okay. So this process is known as shape training. Shape training. And why it is called shape training, it will become clear to you in a minute. So now, after the shape training, if we stretch this wire, you know, you take this wire and you pull it, so it will become long. And then if you heat it slightly in the sense you just heat it up to 40 to 50 degrees centigrade, not much, then this wire will contract to the length at which it was strained, means at which it was heated. So this gives you a property of actuation. So what we do is, at the top, those two wires that you see, they are trained at that length. And they are stretched and then they are bolted on this plastic sheet. Now, we pass current through this wire in a controlled manner. Controlled manner means through a microcontroller, we pass current through the top wire. So if we pass current through the top wire, they get heated up slightly, and as they get heated up, they contract. When they contract, you know, if the top wires become small, what happens to the whole thing? What will happen? You know, if there is wire on the top and it contracts, then it will become like this, right? And then we pass current through the bottom wire alternately, so then it goes like this, and it basically goes up and down like this. So this you can see in this video over here. So this pin, you can see that by passing current alternately from left and right, there will be some movement. Now this movement can be used for moving the tail fin of the robot. So what we did, we took this pin and we put it behind a box, which you can see over there. Within this box, we kept a battery, we kept a microcontroller, and we programmed this microcontroller to pass current alternately on each side of the fin, which is behind it. So the overall result is this. It becomes like a fish. The key challenges here are that how do we seal, you know, because the front part houses a lot of electronics. So those electronics should not come in contact with water. So the sealing and programming of the current through both the sides, those things are the key challenges. But this is how we develop the fish, Carnegie-form fish-inspired robot. So with this robot, we were able to get bending angle of about 30 degrees. And with a power supply of 9 volt and maximum current of 500 milliamps, we were able to generate a force of about 4 Newton. So that brings me to the next type of underwater robot, which is buoyancy regulated robot. Now, if you remember, we discussed that if the fins are used for locomotion, then a lot of energy gets spent to overcome the drag. So instead of that, buoyancy can be used. right? So here you can see this is the robot that we built. You can see that this is made out of very simple rudimentary boxes, lunch boxes, right? At the top, what you see is inflatable membrane, right? So this inflatable membrane is made up of latex, you know, like it's a stretchable sheet. And inside the top lunch box that you see, top lunch box, we keep acetone and heating element. In the middle, we have controllers, and at the bottom we have batteries. So this controller will heat the heating membrane, and with that the acetone vaporizes, and because of that the inflatable membrane is filled up of vapor. And because of that, the buoyancy of the system increases and it starts floating up. And when we want to bring it down, we just stop heating. If we stop heating, this liquid, this vapor gets liquefied and the mass becomes more and it comes down. So here you will see a demonstration of that. You can see when we want to take the robot up, on the right hand side you can see, we heat, and because of that heating, buoyancy increases and it goes up. And when we want to bring it down, we simply stop heating. As we stop heating, it the acetone liquefies, and then the whole thing comes down. And in order to make it float or hover, which was happening, we just keep the heating rate same as the condensation rate. So this way you can actually make this robot quite controlled hovering. Then let us now look at next type of robot, which is alligator inspired robot. So these alligators are very commonly found amphibian creatures, right? Amphibian means something which goes on ground as well as water, right? So these, if you look at the legs of these creatures, you will see that the joints are such that their axes are perpendicular, okay, are orthogonal. So just based upon that intuition, we designed our robot. If you see this picture, it will become clear that how we have taken the inspiration from the real alligator proportions and we designed our robot. So this is the entire CAD model of the robot. In the middle you can see the fabricated robot, the actual robot. And this is how we program the robot's locomotion. So you can see here that we run each of the joints. There are in all 12 motors. So there are 4 legs, and on each leg there are 2 joints. So 2 into 4, 8 motors running 8 joints, and then there are 4 motors on the body, making the body undulate, like 1 on the neck, 1 on the body, and 2 on the tail. So 12 motors are actually actuated by means of Arduino. So overall power requirement is 3300 mAh for this robot. Here you can see the working of the robot. So you can see that this robot looks very much like an alligator, real alligator, right? Its movement is, it involves the body undulations as well as leg movement. If these robots are properly camouflaged using the shape of a real alligator, then we can actually use it in some surveillance applications where they can just look like an animal, but actually they will be equipped with cameras and other sensors like microphones and so on and so forth, say for border surveillance applications. This is another variant of this robot where instead of just 2 degrees of freedom, we are putting 3 degrees of freedom on each leg. So this is the CAD model of our robot, and these are all the mechanisms. Here you can see how this robot works. So because of the 3 degrees of freedom on each leg, now it can actually climb steps. It can climb stairs. So all the motors are programmed in such a way that they perform a synchronized movement so that the robot can actually climb on the stairs. Alright, so that's about a lot of bio-inspired robots that we developed in our lab. Now let me change the gear to some other robots that we developed which are at micro scale. You know, 1 micron is 1,000th of a millimeter, right? 1 micron is 1,000th of a millimeter. 1 millimeter is 1,000th of a meter, and 1 micron is 1,000th of a millimeter. So the key motivation behind doing this work is to perform cell manipulations. Like if you have cells under a microscope and you want to actually move that cells in a particular way, then how can you do that? So for that we wanted to develop a robot. So this is the overall idea. Let us say that green stuff that you see here, the green ball, is a cell, a biological cell. And the blue object that you see there is an iron particle, small iron particle, like you might have seen those iron dust. So it's a small iron particle. You won't be able to see it with your naked eyes also, because these are very small. These are of the order of 50 to 100 microns. And you know what is 1 micron now. So now let us say we keep these 4 electromagnets around it, okay? And each electromagnet has these current going through that which we can control, okay? So if we control this current in a certain way so that the iron particle moves. You see, when you change the current, there is magnetic field in this environment, and because of that magnetic field, the iron particle will move, but cell will not move, right? Because cell is not magnetic. But this iron particle will push the cell, and it will take it to a particular location that you want. So it is like, that small hand, micro hand, which is taking those tiny objects under the microscope from one place to another place. This is the basic concept. I'll show you how it is implemented now. So in order to implement it, what we do is we observe the scene via a microscope. We put a camera on this microscope, and then we perform image processing, and from that processed image we decide how the current through these coils should change. And then we perform this operation, right? So again, math I will skip. So, this is one typical image that we get from the microscope. And we perform image processing on that. With that, we determine the location of the cell and the robot or that iron particle, like this. So basically, this is the overall logic that we use. If you see the top figure here, that brown object is the robot, and that empty white object is the cell. And we want this robot push the cell to the cross or the goal location. So in general, 2 scenarios can happen. If you look at top, there is a misalignment between the robot or that brown object, white object or the cell and the goal. If they are misaligned, then that brown object has to be rotated so that it gets aligned with the goal, like in the bottom object, right? Once they are aligned, then you push or you make this brown object to go towards the goal so that there is a pushing happening to get the cell to the goal location. So this is the overall logic. So this is our overall experimental setup. What you see here at the center, on the right hand side, there is a microscope. It's a stereo microscope. Just underneath the microscope, there are 4 coils. You can see 4 electromagnetic coils that I was talking about, right? And at the center of that coil, there is a slide, glass slide. On that glass slide, there is a drop, and within that drop, there are cells and there are iron particles. And all these 4 coils, the current through all these 4 coils are changed by this controller, which you see on the front. Okay, and at the top of microscope, there is web camera or camera. This camera is streaming images to the computer where the image processing takes place. After image processing, the signal is given to the controller, and that controller changes the current through the coils. So this is the overall setup. The whole thing is built at IIT Patna. So here I'll show you some of the results. These are actual experimental results. Here at the top video that you see, this black particle is pushing this cell in the middle of lot of crowd. Here in the second video, this iron particle is pushing a zebrafish embryo. This is an actual zebrafish embryo, which is being pushed by this iron particle, which is black at the top. And then in the third video, again you can see the robot is pushing these cells, which are non-magnetic, right? Cells are non-magnetic, in a way that a particular arrangement gets made. So all the cells are arranged in a hexagonal pattern. Remember that all these objects are very small. You see that scale bar below. So these particles are all of 100 microns or so. So we cannot see them with naked eyes. These are all seen via the camera, right, and the microscope. And while it is controlling, we are also recording the video of that. So these are actual experimental videos. So you can see that these magnetic field, by the way, this iron particle is moving because surrounding 4 coils, we are actually controlling the current through them, right? So all the ingenuity and the cleverness is in developing that controller, which determines the current through the coils, which is changing to make these iron particles move so that this arrangement is made. Now in the last one, there is flow also present in the environment. Now it is much more complex environment. You will see that these particles are flowing, and the iron particle, which is like jiggling around, that is jiggling around because the magnetic field is making it stationary. Okay. Here we have also developed a lizard-inspired surveillance robot. So here you can see this lizard at the top. We took inspiration from that, and then we developed a robot which doesn't have a tail like lizard, but it climbs on the wall. So I'm going to show you that. So this lizard is climbing, is sticking to the wall using pressure sensitive adhesive. Here the cleverness is in design of this mechanism, which can peel and stick the paws on the wall in a synchronized manner. So in the second video, you can see at the bottom there is a payload attached, 20-gram payload. So even with that payload, it is able to climb. Now, when we put a virtual camera, so this is a simulation of the same robot, right? Simulation means a computational model. So you can see that robot is climbing on the wall, and by using the onboard camera, the camera that is sitting on the wall on the right hand side, what robot is able to see, that we can see, right? So the idea is that if in a scene, you know, where let us say terrorists are holding hostage, so we can send these kind of robots, and these robots can very quietly get the images from that scene. So then we tried out this on a real robot. We put a camera on the real robot, and you can see on the right hand side that robot is moving up. On the left hand side, what robot is able to see, that we can see here. Then we also tried this robot on other environments. Here you can see we used this robot on a tall 4-story building on a glass facade. So this robot is able to climb on a glass facade like this. Then we also tested this robot on solar panels. So you can see that it can climb on that. So there are various verticals that can be derived. You know, these robots can be used for surveillance, but they can also be used for cleaning operations on difficult to reach regions, like, you know, tall glass facades on the exterior of the building, or tall solar panels, and so on and so forth. So we then started developing some more applications around this robot. So here you can see the robot operating in a virtual environment, like a room, right? So you can imagine that a bunch of these robots are on different walls, and they are acquiring images. And these images can be combined together to develop the 3D map of the room. Again, you know, reinforcement learning can be used for solving such problems. Here you can see use of deep learning to identify weapons in a scene. So in this, in the left scene, you see this is captured using a camera outside, and on the wall you can see the robot, and what robot is able to see is shown on the right hand side, right? And by processing this image, you can see that the weapons are recognized. Obviously, this is not a real hostage scenario. We just enacted it. Our students enacted these. Like, you know, they use fake guns, and they dress like terrorists and hostages. But in this scene also, through our system, we are able to demonstrate that we can identify the different types of weapons in a scene. So we actually created a lot of data, and we are putting it into open source for other people also to work on this data. Besides this, some other exciting research work in our group. So, you know, there is a lot of waste that we generate in our cities, in our different places, right? And if we look at particularly our Indian scenario, most of this waste is not separated, not segregated. Like, I don't know about your city, but the city where I am from, even if we segregate things, a truck comes and they mix everything and they take it to a dump yard and they put it there, right? Now, there are waste pickers who go into these dump yards and they pick up the useful objects, like, you know, some metallic objects or plastic objects from that waste, and then they sell it, right? So this is done to recycle, and they also can make some money out of it. But this is highly inefficient and dangerous operation also, because going into the waste that exposes people to toxic and pathogenic environment. And also with the rate at which the waste is getting generated, this human segregation is not possible to catch up with the waste getting generated. I don't know if you have seen around many big cities like Mumbai, Delhi, there are heaps of, mountains of garbage that are getting generated. Have you seen that? There are pictures of that, right? And this mountain is growing every day. It's not that it is reducing. And there is a lot of useful material inside it. But who is going to go and, dig it out? It's like I don't want to say gold mine, but it's like a mine. You can mine it to get some useful items, right? So, can we use robotics to solve this problem? That was the key, starting point of this quest. So, the mixed waste, as you can see in the central picture, a lot of people go there and then they do scavenging of useful material. There are metal, plastic, paper and other organic substance that could be used for many useful applications. So this is our approach, where what we are doing is we take this mixture of waste, we put it on a conveyor belt. This conveyor belt moves and the robot, first we identify different useful materials like you can see in the inspection zone, and then after that the robot picks objects and places them into respective bins. It will pick up plastic and put into plastic bin, and this way it can segregate. Now, you see, the trouble is that you cannot use regular cameras for identifying objects. You know why? Say if you have an aluminum can which is say red colored, right? And you have a plastic can which is also red colored. How will you distinguish between these two? There's no way, right? So what we did, we developed a new technology based on thermal imaging. So thermal imaging is basically the same imaging you might have seen on airports. They are used for identifying sick people. You know what I'm talking about? Like on airports, on international airports, to find people who have higher temperature, body temperature, these thermal imagers are used. So these thermal imagers can actually find out the people who have higher body temperatures, right? So these are done using what are called as monochromatic images, right? So if you see on the top right, that's an example of a monochromatic image. So thermal images are infrared images which will show more white region if temperature is higher and black region if temperature is lower, right? So that's why it is monochromatic, means there is only one channel, unlike RGB or colored images where there are three channels. Here there is only one channel. But the advantage here is that, say, you cannot recognize between red colored aluminum and red colored glass, right? Or red colored plastic. But if you heat an aluminum which is red colored and a plastic which is red colored, both will radiate differently, right? I mean, if you put two objects in sun, right, and then you touch them, two different materials, there will be their radiation properties will be different, right? So we use this emissivity. So what we do is we heat the waste to up to 45 to 50 degrees, and then we acquire thermal images, and then we use KNN based algorithm, machine learning algorithm, right? So K nearest neighbor algorithm. So you can see that with K nearest neighbor algorithm, we can actually train different materials. So we are able to now recognize plastic, we are able to recognize metal, we are able to recognize glass, and so on and so forth. So once that is recognized, then we send it to the robot zone, picking zone, and then robot picks and places it into different bins. So this process can continue, and this way we can actually segregate different useful materials out of mixed waste. So here you can see a video. So different types of waste materials, in fact different types of recyclable materials are recognized, and they are segregated by the robot into different bins. So we have this KUKA KR3 manipulator, which has a small work area, small workspace. So that's why the number of waste materials, number of recyclable materials are fewer in this case. But if we have a bigger robot, then also the same approach will work, right? So in order to simulate that scenario, what we did, we cannot have a bigger robot, so we used the same robot, but we used smaller objects and then classified them, segregated them. In fact, this segregation strategy, like the sequence that we should use to segregate, when we use randomized and when we use our optimized technique, we found that our optimized technique can actually segregate things much faster also. Even if we can save 1 or 2 seconds in these kind of operations, because these operations are going to run 24/7, right? So even if you can save 1 second, you can actually save hours on the robot, and 1 hour saved on one robot means thousands of rupees, right? So this way, if there are multiple hundreds of robots operating, then you are actually saving crores of rupees actually. So with that, I would like to conclude my talk here. I thank all my students who work very hard to get all these research work realized. All the ideas that are there in my head are actually realized by my students, so I thank them. I thank my collaborators in my institute who helped me with different things. And of course the sponsors of the research, SERB, DST, IIT Patna, for helping with funds that helped me with developing experimental setup, supporting my students, and so on and so forth. And of course, thank you to all of you for very patient hearing, and thank you to Nims management who invited me to share my ideas. Thank you.